Hello and welcome back. The last video on the section of higher order derivatives is going to be looking at what do derivatives and maybe even second derivatives or higher even mean. So one thing that we should be keeping in mind is that the derivative of a function is the rate of change of that function. So it's looking at how fast is this function changing. If we have a constant function, it's not changing at all, so its derivative is just going to be 0. The derivative of the constant is 0. If we have a straight line, then the rate of change of the function is going to be constant. The derivative of a straight line is just going to be its slope, so it's going to be some number. But if we start having a function that's going up and down and doing all sorts of crazy things, the derivative is also going to be changing a lot, and it'll be fairly interesting from that perspective. The second derivative, if we take the derivative of the derivative, it's how fast the rate of change is changing. And when we think about, okay, if we have a rate of change and it's changing, well, what does that mean? I think the best way to explore this is to look at a very common second derivative in say physics. So if we have s of t, I'm not sure why it's normally s, but it quite often is. This is usually what we use to describe the position of, let's say, an object, or say like the distance some object has traveled. The first derivative of position is the rate of change in position. So this is how fast something's position is changing. Well, that is its speed or velocity. I suppose technically it's not necessarily a velocity if it doesn't also have a direction associated to it. But yeah, its speed or velocity is going to be how fast something's position is changing. But if we think about your speed changing, maybe you're speeding up, maybe you're getting faster. Well, that's simply acceleration. And so if we have position, we can just describe something position. But if we know its position at all time, we can calculate its velocity. We can see exactly how fast is it going at any time. But if we know exactly how fast it's going at every time, we can then calculate its acceleration. We can know how that speed is going to be changing. We can actually take higher derivatives of this as well, and these have been given some funny names, like I believe the third derivative of position is called jerk, and maybe the fourth is yank, something like this. But ultimately, I feel like these first three are going to be what's most important for us in this class. So let's do an example. An object in free fall roughly has a position given by the following equation. So s of t, the position, is going to be s naught minus 4.9 times t squared. This ignores things like air resistance. So for instance, if you were falling but had a giant parachute, this would not be the case. This is sort of assuming that you are essentially a spherical object that's falling in a vacuum, which might not be real, but it'll serve our purposes. And s naught is going to be the initial position. Whenever you see naught on the bottom, the 0, quite often this means where this was at the start. So for instance, this particular equation assumes that you were stationary at the start, and then you've suddenly been let go, and now you're just falling. So you're starting not moving at all. It's not as if you've been thrown up in the air or thrown down toward the ground. You've just been suspended and then let go. So we have no initial velocity, but we do have some initial position, and our position is going to we would assume decrease over time. As in, we're going to get closer and closer to the ground. So let's find out. So we have our position is going to be s naught minus 4.9 t squared. So let's find our velocity. And the velocity is normally going to be v of t, but we can write that as the first derivative of our position function. The derivative of a constant is going to be 0, so the derivative of s naught is going to be 0. I might as well just write it down. And then I've got minus 4.9 t squared. Well, I have the if I have a constant times the function, the constant hangs around, but then the derivative of t squared is going to be 2t. So negative 4.9 times 2, that's going to be negative 9.8 times t. So one other thing to keep in mind is that we know that position and velocity are measured in different units. So it's important to keep in mind what these units are. I don't specify units up here, so let's sort of in hindsight say that our position is going to be measured in sort of meters. So our position is going to be s naught minus 4.9 t squared meters. So our velocity, when we take the derivative, this is going to be meters per unit time. If we're taking the derivative with respect to time, we're looking at the rate of change in our position over time. So maybe we're measuring time in seconds. So this is going to be meters per second. It could be that we're measuring position in feet and we're measuring time in hours, in which case it'd be feet per hours, but let's assume that we're reasonable people and we like meters and seconds. Okay, so we found the velocity, and one thing to notice about the velocity is that this is always going to be negative, meaning that we're traveling downward. So this makes sense. For this to be describing our position, we're always traveling downward. And now let's find our acceleration. And again, our acceleration is normally written a of t. The acceleration is the derivative of the velocity. It's how our velocity is changing. But velocity is, again, just a derivative of position. So acceleration is going to be the second derivative of position, which means that we're just the derivative of velocity here. So the derivative of negative 9.8t is just going to be negative 9.8. Okay, so what are our units? Well, we're looking at change in velocity, and velocity was measured in meters per second. Oops. So this is going to be meters per second. But if I'm taking meters per second dividing by seconds, this is going to be the same thing as meters per second squared, which makes sense if you've taken some physics classes or some engineering classes. This should be somewhat recognizable that acceleration should be measured in meters per second squared. And also, when we look at this, we see that we have negative 9.8, so we have a constant acceleration. And this is the case in physics, in the real world. This is, again, ignoring air resistance and whatnot, but Earth's gravitational pull causes objects to accelerate at a constant rate of acceleration, negative 9.8 meters per second squared. So this does feel like a reasonable formula for the position of an object. So by taking derivatives, we can easily see what something's position, velocity, acceleration is, but it doesn't have to be. So for instance, let's say that we have where a tide is coming in and out at. So this is like like how far in the tide is, and we can see that. And this is not a real graph, by the way. This is just something I've made up on the fly. And we have this shape, so we can see how fast is the tide coming in, at any point in time is going to be the derivative of this guy. And if I haven't given us a function and we need to find the derivative, well, the derivative is just going to be the slope of the function. So for instance, right at the beginning, the slope of the function kind of looks like that. So this is a positive slope. So the tide should be coming in. It's getting higher and higher. Up here, right up here at the top, we have a horizontal slope. Our derivative is going to be 0. So right up here at the peak, the tide won't be coming in any further and it won't be going out. So our derivative is going to be 0 there. And then down here, our derivative is going to be negative. It's not a very good tangent function, but oh well. The tide is going to be going out. It's receding. And if we look at what's happening here, our derivative is changing from positive to 0 to negative. So over this section here, we're going to have a negative second derivative. And again, how do I know that it's a negative second derivative? Well, the derivative is changing, is trending in a negative direction, right? It's going from positive to 0 to negative. So our second derivative is going to be negative over this section. But what happens over here? We start with a negative derivative, and again, when the tide goes all the way out, it's going to sort of pause for a second, and where the tide isn't going out any further, and it changes direction, and now it starts coming in again. So again, the derivative here is negative, but the derivative becomes 0, and then the derivative becomes positive. So what's happening over here? We're going to have a positive second derivative. And this is because our second derivative is changing, so we know it has a non-zero derivative, so the derivative of the derivative, and the derivative is changing from negative to 0 to positive, so it's increasing, it's getting bigger. That means the derivative, the rate of change of the rate of change, is positive because it's getting bigger. So we can do a lot of stuff analyzing just the shape of graphs. And one final thing that I want to mention is if we're looking for a maximum or a minimum, this is quite often done by saying, okay, at the maximum, the derivative has changed from negative to 0, and it's going to go down to positive. So right exactly at the point where the derivative is 0, it's not going any up, it's not going up anymore. So that means that we have achieved our maximum. So down here, we know that we have achieved a minimum because our derivative was negative, so it means that we're going down. We've hit rock bottom. We've hit the exact bottom when our derivative is 0, and then after that, the derivative has started to go up again. And this is something that we'll look more at in the future as well, but you can tell where a minimum and maximum are just by looking at the derivatives. And in particular, if you know the second derivatives, we can tell the difference between a maximum and a minimum.